All right, welcome back, everyone. Today, we're going to be diving into learning models. We're going to be taking a step away from our tech stack today, and we'll go back to it tomorrow, more than likely. But today, we're going to kind of not necessarily data dump everything that we've learned, but we're going to completely switch topics into more of how do AI models actually interact with our programs, or what is it that's going on when you go to Netflix and you get a recommended for you list of movies, right? Like, how is it that that algorithm or something inside of this tech stack is able to grab a list of movies and provide some suggestions? All right, so first we're going to go into the history of learning models or how learning models kind of come about or how they function, right? Then reality, learning models is a huge, again, boxes inside of boxes, right? And when I'm talking about learning models, I am talking about AI. Now, the most common AI that everybody talks about nowadays is, of course, something called a large language learning model. This is called an LLM, right? And the way this works is essentially ChatGPT, right? So ChatGPT, I can talk to it, I can ask a question as generic as possible, and the algorithm will, or the AI will return a response depending on the data available to said AI. Right, so this is kind of what we're used to or what we've been hearing in pretty much the tech industry for the last couple of years now. It's just what is ChatGPT doing, or what's the new version of ChatGPT or the other AIs out there, and how do they work, and why are they so important, and all their dynamics, right? Like it can provide code, and I'm sure all of you know ChatGPT essentially has access to like older versions of the internet and all that public data. That's essentially how it builds its responses, and it also builds its responses by learning from us telling it, hey, this is wrong. And when we specifically tell it this is wrong, this is the correct answer, if enough people continually do that to ChatGPT, then eventually ChatGPT will learn, oh, this is the incorrect answer. This is actually the acceptable information. And we'll go into how that works later on. But that's kind of the more, um, I guess, attention getter that we see nowadays. But it's actually not the most common implementation of a learning model. Now, there's a couple of other learning models, and these are called classification learning models. Now, classification learning models come in three different types. We have a binary classification model, which essentially we feed data or feed a series of data, and it returns whether said data evaluates to true or false. So that's a binary model. Next, we have a multi-classification model. Excuse me. So there is a multi-classification model, and then there's one more, but we will not talk about the last one. A multi-classification model. And this one will feed a series of data and determine out of multiple options which data best correlates to one of said options. All right. And then we could give an example about these two. So, for example, our binary model, which is just essentially evaluating if something is true or false, right? Um, if we think about a picture recognition, we can feed a picture to an AI model and say, hey, is this picture containing a tree? And what the AI is essentially going to do is it's going to break down every single one of those pixels into a series of data points, right? And it's going to then evaluate all of those data points and return true or false, whether, hey, there is a true in this there is a tree in this picture, and this is evaluating to true, or no, there is not a tree in this picture, and then evaluates to false, right? Now, moving back into this the multi-classification and thinking about picture AI models, there's the classical exercise of training an AI to recognize whether it is receiving a picture between the numbers of 1 through 10. When that happens, it's going to break down every single one of those pixels inside of that picture. It's going to recognize the contrast, whether it's black to white or white to black. And it's going to try to draw out a line of, hey, this is how this is working. This is the lines that I'm able to recognize. And then it's going to determine out of the options between 0 to 9, which is representing 1 through 10, which one of these options does this picture best fit? And then it will tell us, oh, well, this is the number 7, or this is the number 8, and over again, right? Those are kind of the two different types of AI that are, or learning models that are very known and typical to interact with. Now, we're going to be diving deep into these classification learning models. We will not be interacting into how to build a large language learning model. That would take a considerable amount of time to talk about how this works and what's going on in everything inside of that Pandora's box. So we're going to start small and start with our classification learning models, specifically into our binary models, and then moving into multi-classification models. Does anyone have any questions over what I've covered up to this point? Okay, great. Doesn't seem like there are any questions. So we're going to go ahead and move. Excuse me. We're going to go ahead and move on into how is it that these learning models work, right? Well, just like we talked earlier, I mentioned, hey, we might receive a picture here. And inside of this picture, maybe we want to determine, is there a cloud inside of this picture that's holding a nice, beautiful sky there, right? So let me see if I could, that's a nice color. And there you go. All right, so there's my picture of the sky that has a cloud. And I want my AI to be able to determine whether there is a cloud or maybe determine what kind of cloud this is. That would be a multi-classification. But in this case, I just want to determine, hey, is there a cloud inside of this picture? Well, what is it that it's going to do? What's my AI going to happen? It's going to, one, take this picture and it's going to break it up into a series of small data entries, right? Let me make that into a medium. There we go. And small. Oh, jeepers. All right. It just continuously breaks it down over and over again. Let me try to move this out of the way. It's going to break it down into look something like this. All right, where rather than evaluating an entire picture, It's just looking at each individual square. And then each one of these squares is going to get designated an actual numeric value. Now, when it comes to pictures, the numeric value that AI typically utilizes is the RGBA value, which we know is the color standard for what comes out of every CSS, right? So it takes a look, it looks at what the color standard is between red, green, and blue in each individual picture. It analyzes it and then comes up with a number for each one of these tiny squares. It's going to be better if I do it this way. All right, so it comes up with comes up with a number for each one of these squares to try to figure out what the value is for them, what their balances are. And each one of these squares will end up being represented by something like, hey, this is going to be a list of 1.0, 2.3, and 3.4, right? So that's the RGBA value. And that's just one square. The next square may be represented by something like, hey, this is 1.5. This other is actually holding a cloud. So because it's holding a cloud, it kind of evaluates to 5. And then maybe something like a 0.2, right? Because there's a little bit of white in there as well. And that's all just representing one tiny square. Now that's how these numbers get created and how this picture gets broken down into a series of data, right? So now we have our series of data points, which is the RGBA value for each one of these pixels inside of this picture. Well, now what happens here? What's the point of this data and how can my AI utilize this data? Well, what's going to end up happening is it's going to get fed into something that kind of looks like a funnel. Let me see if I have a shape here. I do not. That's okay. Now this funnel is a representation of our learning model or our AI. So all of these data entries for every single one of these pixels are going to get fed into our funnel. And what our funnel is going to do is it's going to break down the probability for each one of these one step at a time. It's going to take all of that jumbled up data, and at the very end of said funnel, it's going to come out with a number between 0 to 1. And from there, we can evaluate, hey, if result is greater than 0.5, then this is equal to true. Else, it would be equal to false. All right, so our AI takes the entire image, breaks it down into individual data points, gets fed through this funnel, and at the very end, we're just going to receive a numeric value between 0 to 1. And from there, we'll determine, hey, if the result is greater than 0.5, then the answer is true. Otherwise, the answer will be false. And that's pretty much how the AI breaks down an image to make an accurate prediction, right? Like these are all predictions. They're not actually learning anything. All AI is statistics. It's literally just learning a ridiculous amount of math in the background to figure out the probability of this being true or it being false. All right. Does anyone have any questions over this process? Let's hear it, Juan.
For that number 0.5, will that, as it gets fed more data, eventually start changing if it notices a higher fail rate at 0.5, will it start moving up to like 0.8, for example?
So what we're evaluating for the zero point 0.5 is just whether something is closer to one or zero, right? The result that comes out of here will be anywhere between zero and one. But what we will ask to determine whether it's true or false is if it's closer to one or if it's closer to zero. Does that make sense? Okay, awesome. I see the head nods. Any other questions? Okay, I don't see any other questions. So let's go ahead and open up this funnel. What does this funnel actually look like and how does it work? Well, we have a pretty handy dandy image here on our curriculum that breaks down what this funnel looks like, right? So now instead of looking at the funnel in the way that I drew it from top left to top, from top to bottom, what we're looking at here is a funnel that goes this way, right? It receives our data entry and it populates an output. And that's what we have here. So the input, which is our image tensors or image data series, it's going to get broken down into something called neurons. This is called a neural network, and it's going to be fully connected. We're going to have a couple of different layers. We have our input layer, which is just essentially where all of our data is being received. And then we're going to have something called linear layers or hidden layers. Now, hidden layers are everything before the activation layer, which is going to generate our output. And all these layers are doing is they're receiving the data. They have something called weights and biases, which is what kind of affects the math as to how these linear layers are going to interact with one another to make a good prediction. So the input layer comes in, it passes it to the next one, does its calculations, it runs some math, and then it passes it to the next layer. That next layer has its own weights and biases, runs its math, and then passes it to the next layer. And that process gets repeated at each individual layer between these three. Finally, in the activation layer, what it's going to do is essentially going to say, hey, I have these three different numbers, but I can only output one single number between the number of 0 and 1. So it takes those three numbers, runs its mathematical function, and it outputs a singular numerical value between 0 and 1, right? So that's essentially how it works now. Now, these weights and biases are extremely important at each linear layer because that's how you train a model. This is how the model learns. If it's wrong, we're going to tell the model, hey, this is wrong. This is the correct answer. And then it's going to work backwards. It's going to say, well, this is the correct answer. This is the output that I made. So this is the calculation mistake that I made at the activation layer. And then it's going to pass that mistake backwards and say, hey, this is the mistake that I made. What did you guys do wrong? And then they are going to readjust their weights and biases and pass that information back, and so on, all the way into the input layer. That way, all of the data is consistently being updated, and that is how our model essentially learns, right? It is getting this is the wrong answer, this is the correct answer. I want you to compare both of these and change the numerical values inside of your weights and biases so that you can actually output something closer to this correct answer. Not the exact answer, but something closer. Does anyone have any questions over the fully connected neural network and weights and biases? We're going to be deep diving into all of this in the next couple of lectures. This is just to get familiarized with the framework, but please know today is an introductory and overview. We will be diving deeper into all these concepts. Okay, doesn't seem like there are any questions. So we're going to go ahead and push forward here. So far we've talked over the history of LMs. We talked about the different types of learning models, how do learning models work, and the learning model infrastructure. Now we're going to talk about Python virtual environments. We've already talked about Python virtual environments a little bit during Django, but we're going to open up this black hole one more time. Right? So Python, we need a way to keep track of our different projects and their different dependencies. And we want to make sure that we keep those dependencies isolated to each one of them. Right. So I made this image here where we have our local machine. If any of you are Mac users, you'll notice that your local machine already came with Python installed inside of it. Right. But that Python inside of our local machine isn't necessarily the Python that we want to utilize for every single project that we create, because we need to have different dependencies for different projects. So here we have an example of three separate projects, right? We have project one, project two, and project three. And each one of them hold their own virtual environments or their own version of Python. Some of them may be using something like the version of Python of 2.1. Maybe this project is created with Flask 1.2 and it utilizes pip2 instead of pip3. It's an old project, but it's still running and it hasn't been updated. So whenever we work in this project, we need to make sure we utilize this Python virtual environment so that we can actually run the scripts without having to debug or run into any issues of updating to the newer versions of the framework, right? If we look at project two, well, this is running on Python 2.15, while the project one was running on Python 2.10. If you don't have a way of isolating these dependencies inside of your virtual environment, well, some of the commands that you wrote in Python 2.1 or 2.10 aren't going to run when you try to execute them with Python 2.15 and vice versa. Now, these are just random numbers. There's not necessarily an actual version there at 2.10 or 2.15, right? And then we have pip2 and pip3. Well, that could be a huge problem if I'm installing things with pip2 for one project, and then I try to install those same dependencies inside of project two, only utilizing pip2, then I'm not downloading the same versions or I'm not grabbing the same versions that I would if I were utilizing pip3, right? And then finally on project three, well, we can see that project three not only utilizes Django, but it also utilizes Django REST framework and Psycho PG3 to be able to connect databases. Now, all three of these projects utilize different versions or different versions of frameworks or even different frameworks altogether. So I need a way to isolate their development dependencies, right? When we were learning about React, we were able to isolate these development dependencies in something called the package.json, right? We had a specific section inside of React that was called dev dependencies. And that's where everything was being stored for each individual project. Well, when it comes to Python projects, that doesn't get created for us. So we have to isolate it utilizing a virtual environment. So now before I go into actually creating a virtual environment here on my terminal and on VS Code, does anyone have any questions regarding the importance of a virtual environment or how a virtual environment works? Okay, great. This should be review because we already covered it in Django. So let's quickly create a virtual environment here. I'm going to utilize python-m vnv dot vnv. And that will create a virtual environment directory here in Intro to Learning. You'll see that I have bin, which gives me an activate script. I have include, which includes all the different packages that I have, and I have lib as well. So let's go into installing, or first we're going to go ahead and activate this virtual environment. So I'm going to change my source inside of my terminal to go into .vnv/bin/activate. And on the left-hand side, I'm going to get these parentheses .vnv. That's going to let me know, hey, this virtual environment has actually been activated, it's functioning, and I'm inside of it now. Now, if I actually do something like which Python 3, it's going to show me that the Python 3 I'm utilizing is originating from my virtual environment. It is not originating from Bash, or it's not originating from Homebrew. There you go. It's not originating from Homebrew, where we originally installed it. It's actually originating from this .vnv. So now I have my Python virtual environment. It's been activated. And the first thing I'm going to do is I'm going to upgrade my pip. So I'm going to say pip install -- upgrade pip. You'll see that pip gets upgraded. I can see that a couple of scripts changed here. So now I have pip. Oh, it's not going to show me where it got updated. Okay. All right, it's not showing me where it got updated, but we installed it and it's been updated and I have an actual pip installed in my virtual environment. All right. Does anyone have any questions or need any help with setting up a virtual environment? Okay, looks like we're good with that. So now that we have our virtual environment set up, we can go into installing something called PyTorch. So let me go ahead and look up PyTorch here so that we can go over to this nice handy dandy getting started tutorial. So here we see PyTorch, and it tells me a couple of things. It's actually super easy to help you set up. We're going to be utilizing PyTorch for building all of our learning models. We'll go into why PyTorch later on. PyTorch gets utilized in a lot of different learning models. As a matter of fact, I believe Tesla utilized them for um, their like image recognition system on the Teslas to be able to actually drive. So it's consistently running, and PyTorch is part of their like learning model tech stack. You could look it up. Super popular, super simple, utilizes a lot of Python, which makes it super easy as well. And it's really nice because it works with NumPy. You can see here that it tells you, hey, we're compatible with NumPy, and it's nice to work with pandas and all those other libraries when it comes to data analysis. So now it tells me, hey, what do you want to utilize? Do you want to utilize all of the brand new stuff that may be broken as well, or do you just want to utilize our stable version? Definitely just want to utilize a stable version. It also helps me with, all right, well, what's your operating system? My operating system is going to be a Mac. If you're using Linux or Windows, make sure you choose those accordingly. For package, where you're going to be utilizing pip, the language will be Python. And the computer platform, if you're running something like a Windows machine, it's going to ask you if you want to run something like CUDAs. For now, just stay with default. That way we can have the same structure for all of us. If you go with something like CUDA, it's just going to make it a little bit faster. But I don't want to run the risk of running into dependency issues with the rest of the class. Stick with default for now. And if you want to experiment with CUDAs later on, after the class is over or, on your own time, please feel free to do so. And then finally, it gives me a command that I can run inside of my terminal to actually install PyTorch. So I'm going to copy said command. I'm going to bring it over, paste it, and install. And it gives me a problem. Could not find requirement, torch vision. Let's see. Pip install torch. Huh. I apologize, everyone. I'm running into an unsuspected issue here. All right. Let's go ahead and take a 5-minute break while I try to figure this out and then come back. Currently it is 9:30. I'll see you all back here at 9:35. All right, everyone. So the issue we were running into was because of the version of Python I was utilizing. Apparently PyTorch is not yet with the newest version of Python. So here it tells us Python, hey, it wants us to utilize between the versions of 3.9 and 3.12. I'm currently using by default Python 3.13, which was the issue I was running into when I tried to install. It was saying, hey, there's no such thing as PyTorch for this Python version. So what I quickly did is I installed utilizing brew. So I ran, where is it? Utilize homebrew here to actually install Python 3.9. Here's the command. I ran brew install Python at Python 3.9. So let me go ahead and send that here on our chat. Now, after installed Python 3.9 and everything was dedicated, I created a virtual environment utilizing Python 3.9. I did that with this command here. So you can see that it's still the Python dash VMV, or excuse me, dash M space VNV. The only difference is I'm specifying, hey, this is Python 3.9 that I want to utilize to create this virtual environment. All right, and then when I come down below, finally, I was able to run this pip install for Torch Vision and Torch Audio. All right, I'm going to go ahead and send this all here on the chat. It is inside of Yankee Questions, and I'll make sure that gets updated in the curriculum as well so that we're all tracking what's going on. Looks like Python just got a new version, and it just happened to be outdated between last cohort and this cohort. So I do apologize for that. All right, awesome. So now that everything has been installed, I have all of my commands and I have PyTorch installed. I actually want to make sure that PyTorch is installed inside of my virtual environment. So how do I make sure that that happens? Well, there's a command that I can utilize in the command line. I can say, hey, Python, I want you to execute the following command. And in the following command that I want you to execute, this is essentially as if I were writing in a Python script. I want you to import Torch. And in the next line, I want you to print Torch version. Right, so I imported Torch. Torch is a class, and inside of Torch, there is an attribute named version. Great. So finally, I close my quotation marks. This is a command that I want to execute in Python. We can see that it's taken a while to process. And then finally, I get an output saying, hey, the Torch version that we are currently working with is 2.5.1. And that's how I know that Torch has been successfully installed into my virtual environment. All right, great. See a question? Go ahead, Owen.
Yeah, if I have a plus CPU on my 2.5.1, is is that because I installed PyTorch wrong, or is that fine?
No, you're not on a Mac, which is why I'm assuming you're getting that extra. Perfect.
Yeah, I
Yeah,
have the same thing.
cool.
So
Sweet, thank you.
Of course. All right. So now let's go ahead and continue moving forward to our next tool, which is going to be Jupyter Notebook. Now, Jupyter Notebook is going to actually be pretty easy to install. We're going to go to extensions first. I'm going to go ahead and look up Jupyter. That will show us the Jupyter Notebook. You can see that I already have it installed. You don't need any of the other Jupyter Notebook things. If you really want to install them, you can, but you really do not need them. And let me actually share this Jupyter Notebook extension with everybody. All right, so there's the Jupyter Notebook extension. Install it into your operating system. And once you have it installed, we can go ahead and move into the process of installing the different commands to actually execute Jupyter Notebook. So now I can pip install Jupyter. You can see that's installing a couple of things for Jupyter Notebook to actually be able to run. All right, so Jupyter Notebook has now been installed. Everything is up to date with Jupyter. And now I can actually, We already did that. The last thing that I need to install is going to be the kernel that will work with Jupyter Notebook. Because we're going to see right now how Jupyter Notebooks work. It doesn't work the same as a regular Python script, right? We can execute different portions of a Jupyter Notebook at a time. So we need a specific type of kernel to be able to execute and keep track in memory of different variables in comparison, depending on how we're executing the code. Rather than going from top to bottom, we're dictating this code needs to be executed, then this code. So now we install the IPY kernel. Everything has been installed. All of these commands are also inside of our curriculum, which let me just send the link to the curriculum as well so that everybody has that available to them. And then finally, we can go ahead and open up a Jupyter Notebook. Well, how do we do that? We can say touch. We're just going to say this is main.ipynb. Right, this is going to be the extension for a Jupyter Notebook is IPYMB. We can see that it comes out with a little icon there. There's my main.ipymb. I can go to it and it gives me, hey, I want you to select a kernel. It's the first thing that pops up to us. We need to select a kernel. Well, I just installed a kernel. I know that. So I just need to map it to this EMV here. All right. So I'm going to click on select the kernel. It's going to tell me, well, hey, where do you want to do this? And then it shows me the different Python virtual environments that I have. Well, the virtual environment that I want to utilize is going to be ENV39 because that is utilizing 3.9. It links it to that kernel. And now I can actually write some Python code. Click on code. I can import which it's going to recognize it because it's linked to environment 39. And then I want to print torch dot underscore underscore version. Well, now how do I execute this file? I'm actually not going to utilize the terminal. I'm just going to click this play button. And there you can see it's been executed once and the output was 2.5.1. And that is the entire setup for installing PyTorch and Jupyter Notebook. I know it was a lot of steps. We're going to take the next hour to make sure that everybody has this in their operating system and that they can run PyTorch well and that you guys understand the proper environment. So at this point, does anyone have any questions before we break up into our rooms to actually go over the installing? All right, Jacob.
Yeah, when you chose environment 39, like I have a few options. Like I have .venv and then like Python 3.10 and then like at the bottom I have like default, but then it's like starred recommended for .venv. I'm not sure because I didn't have the env 39.
Got it. So when it comes to that, you can come to your terminal, run which Python 3, and it's going to show you the environment that you're currently utilizing. So you
Okay.
can copy this entire path if it
Okay.
doesn't populate for you.
Yeah.
Go to select a kernel here, and you can click on Python virtual environments. If it doesn't populate here, oh, it doesn't give you the path option. Yeah, it should populate in here. So you could just choose the one that correlates to the virtual environment down below.
Okay, so you should just copy and paste it in the search thing. Is that
Uh,
how it works?
no, so I put which Python 3,
Mm-hmm.
which one it is that I'm utilizing,
Okay.
right? I go to my kernel, let's say select the kernel, Python environments.
Oh, okay. Just the one that matches that.
Yeah, and then you just choose the one that matches it, of
Gotcha. Thank you.
course. Owen?
I don't know if it's because I don't have Homebrew on my machine or what, but I couldn't brew install Python 3.9.
Okay, if you don't, it's because you don't have Homebrew in your machine. If you're on a Linux or something else, you would use sudo apt get
Okay.
Python.
3.9. Okay.
All right. James?
If my virtual environment isn't automatically showing up in that drop-down menu, does that mean I probably did something wrong?
Not necessarily. Let's see. We can go here. Let's say create environment. Nope, we don't want to do that. Uh, we will have to go into that separately, because now we're running into
Okay.
machine issues. So let me go ahead and pause our recording here. All right. So now let's move on with PyTorch, right? We've talked about a couple of examples about how this is going to get broken down, how essentially what we do in case of an image recognition, we feed it the image, the model will break down each one of these pixels, get the RGBA evaluation for each one of the pixels. It's going to feed that through our funnel here, and then our funnel will essentially go through each of our input layers, run some calculations, and come out with a true or false variable. Now, there's quite a bit of things that we can do with PyTorch. Specifically, the one data structure that we're going to utilize in PyTorch is called a tensor. And a tensor is just a list of lists with decimal numbers, kind of like what we have here, right? Well, where does this data come from, or how can we represent this data? We're going to be utilizing a lot of data from Kaggle. If we take a look at cats versus dogs here, you can see that it gives you a little bit of information regarding the data set, but it tells you, hey, you have to go here if you want to take a look at that a little bit more in depth. Um, let's see, this pizza or not pizza, right? So here's some information about the data set, and it tells you, hey, here's two directories. One is holding all files that are not a pizza, and notice that this data is balanced, right? If we open up this not a pizza, it's just showing me a bunch of different foods that are not a pizza, right? If I go back, oh, went too far back. Let's go back here. And we take a look at the pizza directory. Well, in the pizza directory, we're taking a look at images that are pizza. That is one disgusting looking pizza, but hey, to each their own. And we can see that the data is pretty balanced. There's 983 files for both of them, right? So here's our pizza or not pizza, and they also give us this little piece of information to randomize different ranges of the images. And this is a small calculation just to be able to grab the images and turn them into tensors. But we'll be utilizing PyTorch to actually take a look at these images and turn them into tensors, right? Well, this is just one of the very few examples that we'll be utilizing. There's also something called a water potability. There you go, water quality and potability. I believe that's it. So here in the water quality and potability, this is one of the very few that we're going to utilize. Essentially, what this evaluates to is whether the water is drinkable or not. So you can see that there are many more results for false, meaning that the water is not drinkable, than there are for true. Here's the evaluation between 0 and 1, right? This is going to be our answer. And all of these are the different attributes of water that we'll be feeding as a tensor or a list of decimals to our learning model so that our learning model can learn, hey, depending on these attributes, I want you to tell me without me having to run it through a lab or anything. I want you to use probability or, everything that you know from all of these other data sets that I gave you, whether the water is in fact drinkable or not. All right. So that's how everything is going to break down. Anything that gets fed the into the learning model is just going to turn into a numeric value, and that numeric value is going to get manipulated throughout each linear layer in order to formulate this output, right? And Netflix kind of does the same thing. So Netflix, what it does is it has different categories of things that you watch, such as, whether you like to watch action, comedy. Every film has specific attributes that belong to the film or show. And the more you watch these films and these different tags or attributes become repetitive, well, the learning model that is designed to learn your preferences takes in all of these tags that are repetitively being watched or that have the most amount of content time. That goes through the model, and then from there it makes a prediction as to which shows you'll be interested in depending on said tags. And that's how you get that, hey, this is what's recommended for you. Right? It's all happening through a nice and quick learning model. So now let's start looking at the capabilities of PyTorch and how we can manipulate these numbers and why is it so powerful. All right. So what we're talking about interacting here is a couple of matrices. I'm going to go ahead and make a new code block here just to create a couple of random numbers. Oh, that is not what we meant to do here. All right. So here we're going to go ahead and create matrix. So you can see I can write some markdown at the same time that I can write some code. You can change the order of these as well. All right. So now I'm going to go ahead and import random, which we know just belongs to Python. And I'm just going to create a matrix here. This matrix is just going to be a list of lists where we're going to utilize random.random for in range of 3. And then we're going to do the same thing for in range of 3. This is just going to give me a quick 3x3 list. And then finally, I'm just going to print this matrix so that we can see what we're working with throughout our different iterations. All right, so there you go. I was able to create a quick matrix. All right, it is a 3x3 matrix. Here we can see a list of 3. And what this does is now we have something that we can interact with utilizing PyTorch. Now, let's say I wanted to manipulate to these matrices, right? I have matrix 1. Let's just call this matrix 1, and let's make a matrix 2 as well. So now I have matrix 1 and matrix 2. I'm only printing matrix 1. But let's say I wanted to do some sort of mathematical function. Let's say I wanted to figure out, hey, what's going to happen if I multiply all of the indexes of one matrix by another? Well, that turns into a bit of a complicated concept, right? Because I would have to do some sort of iteration, something that looks something like this. Right? I would have to say, hey, for IDX in matrix 1, and then for JDX in matrix 1, IDX, that's just to iterate through one of the list. Then I would have to go through matrix 2. And I would say, hey, for, and I just realized that this should be range, len. There's the whole messing it up already. Then I could actually multiply them. I could say, hey, well, I want a result to be equal to a list, right? And then I could say list. So I can go ahead and say, all right, result dot append, which is going to be matrix 1 at IDX, index of JDX, times matrix 2 at index of IDX with index of JDX. And I believe this should look something like this as well. Nope, excuse me. Let's do sub result. here. So now I did this whole craziness just to be able to multiply all of my matrices or my two matrices by one another. And I can finally print result. All right, now when I go ahead and execute this, we get one single 3 by 3 where I was able to multiply all of these matrices by one another. But you can see how the code got a little complicated. I made a whole shabam bam. Sure, I could write it in one line here if I really wanted to. I could probably do something like this instead. But even this one line of code is it's pretty intense, right? We're looking at a complicated little nested for loop that's not necessarily going to do our job easy, especially if we're messing with some sort of data set that has a ridiculous amount of attributes. So instead, what we have is something called tensors. Now, how do tensors work? Let's take a look at tensors now. Tensors are an easy way to represent matrices and have easy access to mathematical functions. So for example, what we just did was multiply by each location. Well, let's take a look at what it looks like when we use tensors. We're going to have tensor 1, and that's going to come from torch.tensor. That's just going to be a list of lists as before. So we're going to have 1.0, 2.0, 3.0. We're going to move into 4.0, 5.0. We're going to keep this pretty simple and just use solid numbers. Then finally go to our last one. Yeah, and then we're going to make tensor 2, which is going to be exactly the same thing, but backwards. I'm just going to grab this straight from our curriculum. I'm sure you guys are getting tired of just watching me type things into the VS Code. So there you go. We have two different tensors, and let's see the way that they're being represented here. I'm going to go ahead and print tensor 1. Well, you see that tensor 1 gets represented as a list of lists, but it also drops it. Whereas before, when I had a list of lists, it kind of just falls from left to right. So it's a bit different, right? But notice the power of a tensor really comes in when I want to do something like, hey, I want to multiply both these tensors by one another. If I do tensor 1 times tensor 2, and I multiply them, and I print the result, which might be important, we can see that it's easily able to multiply each one of these. All I had to do was the time sign, and it's multiplying them by indexes. And this is a lot easier than this entire gibberish that I ended up writing up above, right? I wanted to have some readable code. Yes, I could have done it in one line, but because I want some readable code, it takes a couple of lines to make sure that it's actually readable. Everybody can see what's going on. And then I'm able to multiply it. And I myself, as I was trying to build this little algorithm per se, I was getting a little bit lost in what's going on between the different matrices, right? Well, tensors compensate for that. Tensors make it so that, hey, we know we're going to be running a ridiculous amount of math on this. So instead of making you do all the hard work, I'm just going to create this one data structure called a tensor that knows how to multiply these matrices by one another or even add these matrices by one another, right? Because we can just add them together and all of them would give us 10 because they're the numerical order up to 10. All right, I'm going to go ahead and pause there. Does anyone have any questions over how to build a tensor or the power of tensors? That's a good doggo.
So what's an example of where you build a tensor? Like a real life example of because you went on to like how there's binary like calculations where it's just ones and zeros. Like, is this true or is this false? So, what would you utilize that in a tensor at all?
Yeah, you would. So essentially, as I apologize, let me bring this up here. As we mentioned earlier, so all of these, for example, this data set that would come in, this would create a tensor, right? And this tensor would just be a tensor of length of 10 with one, or excuse me, of length of 9. And this would get excluded because this is going to be our answer, right? And these tensors are the ones that would be fed into our model, right? And if we were talking
So
about
all of those variables would be like in a sub list, like we had in our tensor, and then it'd be a list of all of these sub list.
exactly, yes,
Okay.
right. And then if we're talking about images, the image would get broken down to where we get the RGBA color for each one of the sublist, right? And then the massive tensor or the huge data set would just be one list of all the representations for each individual pixel. Does that make sense, Owen?
Yeah.
All right, awesome. What doggo is he talking about? Okay, now we're talking about the doggo. Cool. All right, let me go ahead and check the chat. There's nothing on the chat. Let's go ahead and continue moving forward. So now we were able to add tensors, we're able to multiply tensors, but what else can we do with tensors? Well, we can actually manipulate tensors so that we can take a better look at them or even change their views. Sometimes you have to change the shape of a tensor in order to make it work with other data. We're going to see examples of that as we start building our learning models. But for now, we're more going to explore the tools that tensor have to offer. And then when we encounter a good necessity for said tool, we'll actually utilize it during our curriculum or during our time building models. So let's go into some tensor. Go ahead, on.
What's the difference between a code and a markdown on your main.ipy and b?
The difference between Markdown and code.
Yeah.
So the Markdown will actually create Markdown, like just regular Markdown. I'm not sure
Okay.
how else to
It's
describe.
not. It's just like a README kind of sort of just
Exactly.
to display what that code's actually doing below it.
Yes.
Okay. Cool. Thank
So
you.
I guess I should go a little bit into why Jupyter Notebooks came about. So Jupyter Notebooks are mainly utilized to share like scientific research. So sometimes when people want to explain and they create graphs using something like Matplot inside of Python, they usually utilize Jupyter Notebooks because in that way they can write their notes explaining, hey, this is what this code block is doing, this is what it's showing, and this is why we have this hypothesis. And then they show like all the research under it. That's the main reason for Jupyter Notebooks.
Do the same thing with R Studio with like R Markdown files, so you can make your data and your code like presentable and digestible chunks and stuff.
Nice. I didn't know that. Thank you, Jacob. All right. So now we're going into tensor manipulation here. The first thing that I want to cover is going to be how do we view a tensor. All right, so I'm going to go ahead and print tensor1 here. When we run this, we can see that tensor1 is a simple list of 3. Well, in this next iteration, what I want to do is I want to reshape this tensor. And what I'm going to do is I'm going to call tensor1. I'm going to change its view to be a 1 by 9. Now I'm going to print reshape tensor. So now our original tensor was a 3 by 3, right? I called this set tensor and notice that this is not destructive, right? I can still print tensor1 and tensor1 will still hold its original dimensions. So this is not destructive, it's constructive. It is creating a new value that is being saved in the variable reshape, right? So it's not destroying the original value of tensor1. I am simply telling it that I want you to grab this 3 by 3 grab all of those values and reformat it to where it's a singular tensor of 9 values. And then we can reshape it. All right, so that's our view attribute. Next, we're going to go into slicing. Now for slicing, we still have tensor 1. I'm going to grab slice tensor. I'm going to call it tensor 1. I'm going to say, hey, I want to manipulate through set tensor and print that out. All right, so I grabbed all of the values from index 1. All right, so here's tensor 1 at index, oh, excuse me, 258. Nice. So it grabbed all of the values from each one of these, and it grabbed it at index 1. So 0, 1, which is the number 2, 0, 1, which is the number 5, 0, 1, which is the number 8. And now we get the tensor of 2, 5, and 8. All right, so slicing works a little bit different when it comes to tensors in compared to what we're used to. All right, we can also run some Boolean evaluations or comparables. We can say, hey, I want to find out if tensor 1 is greater than 5. Let me go ahead and print that. So let's go Boolean tensor. I think there's a mistake in this part, but oh, there you go. All right, so 6, 7, 8, and 9. Let's see. So it went through the entirety of tensor 1. I asked it, hey, which one of these is greater than 5? And it grabbed 6, 7, 8, and 9, I believe. Right, so I went through the entire tensor, built a new one, all of them evaluating greater than 5. All right. Now let's go into concatenating tensors. We have tensor 1 and tensor 2. I want them both to be together. So I'm going to concatenate. I can't spell that, so I'm going to do that. And this is going to be a simple torch.cat. So this is a function that belongs to torch, and it takes in 2 tensors. In this case, tensor 1 and tensor 2. And I don't want to change its dimensions, so I'm going to put 0 to ensure that it doesn't change any of the dimensions coming in. All right, so there you go. It was able to mix our 2 tensors that were 1/3s, and now I turned it into a 1/6. And now I have a tensor of 6 sublist. Let's hear it, James.
When you are setting dimension equals 0, what I don't understand what that is. I was wondering if you could explain it further.
Yeah, absolutely. So dimension 0, meaning I don't want to change what's happening inside of it, right? Notice that when I put, hey, I want to do dimension 1, what it did is it took tensor 1, which was 1, 2, and 3, and tensors 2, which was 9, 8, and 7. Those were both the first values or the first tensors being included. I said, hey, I want you to keep the first dimension, meaning I want you to keep it a list of 3, because that's what we originally had, was a 1/3, right? So in order to do that, what it did is it took the 2 first tensors and mixed them into 1 of 6. And that's how we end up with a 3 of 6. Does that answer your question, James?
Yeah, definitely. Thank you.
Of course. All right. And now let's go into stacking. So stacking tensors for new dimensions. Let's take a look at that. This is, again, something that comes from Torch, and it's called stack. We pass in tensor 1 and tensor 2. And then again, we pass in a dimension. Let's do dimension 0 for now so that we can see what it looks like, and then we'll do dimension 1. So we do stacked tensors. Okay, so it stacked them, right? It still turned into a list. It mixed both of the tensors, but now it's a tensor of two tensors, right? Instead of mixing them together and having just one single sublist, now we have two sublists inside of one another. So that's not necessarily what I want. I'm going to change that to a dimension of 1. And now when I run this, we can see I have a sublist of sublist, but it's broken up into twos. Right? So that's what it means by stack. I am sublisting them and then creating more subtensors inside of that master tensor. It's all just putting more boxes inside of boxes. Now, this stacked isn't necessarily something that you're going to utilize very often. It is there for us to have around, but know that this is a very rare tool that we're probably not going to encounter very often. Owen,
What would be a use case for stacked tensors?
could you say that one more time, Owen?
What would be a use case for stacked tensors or for stacking tensors?
Yeah, so a good use case for stacking tensors would be something like data balancing, right? If you want to make sure that there's a specific you have a specific set of attributes that you know are going to evaluate to be false, and you have a specific set of attributes that you know are going to evaluate to be true. Maybe you want those to be paired together as they're being fed through your model, or maybe you created a model that even though the data is set up to where there's 9 attributes, you need it to be smaller subsets of tensors, and your model can only accept maybe 6 attributes at a time. That's when you would stack it so that you can actually just have smaller tensors that you can feed through the model. Does that answer your question?
Yeah, so this would be kind of used for like the training phase. From my basic knowledge on neural networks, like there's a training phase to train your algorithm, and that's what this would be really used for when you already know what the answer is. So you're returning that answer to the model to
Yeah,
teach it.
I think this could be used either during the training or the data preparation phase. Either both of those would be something that would be acceptable for this.
Okay, thank you.
Of course. All right. Awesome. So now let's take a look at a couple of different tensor methods that are available to us. All right, so the tensor methods that are available to us, there's going to be the simple tensor shape that we can print, and actually we don't even need to print this. By running this tensor shape, it's going to tell me, hey, this tensor is a 3 by 3. Okay, great. Well, what other things do we have here? Well, I can run something like tensor size, and tensor size will also return the same response. It's just essentially telling me what exactly it is that my tensor look like, whether it's a 3 by 3 or not. Now, why could this be useful? Right now, we're messing around with a tensor that's 3 by 3. But if you're interacting with a data set that maybe it's hey, this is 10 by 50 or 10 by 45, and there's a considerable amount of data going on there, I don't necessarily want to go and count each individual square from left to right to figure out what dimensions I'm working with. So instead, I would just utilize this size or shape attributes to be able to see them. All right. There's also the tensor endem. So let's do tensor endem. And let's see what that does. So tensor endem returns 2, and that's just telling me the number of dimensions. So this is a 3 by 3, so it is a 2-dimensional tensor. There's the data type. So we can run tensor1.dtype. And this one we will be interacting with quite often, the dtype, because we need to ensure that all of the data, including the answer, is following the correct type. And that's not always going to be the case when you're interacting with different data sets. Some data gets collected in different ways. Some of it gets evaluated as solid numbers. Some of it gets evaluated as float 32 integers or float 32 decimal points. Some get evaluated as float 64 decimal points. You just have to make sure that they all match the same data type before you actually start interacting with them or feeding them through a model. All right, now we have unsqueeze. So let's do unsqueezed tensor, and let's go into tensor 1 and run the unsqueezed argument. And here we can do unsqueeze 0. Oh, probably should see the unsqueezed tensor. There you go. All right, so unsqueeze 0, you can see that it got nested inside of another tensor. If I do dot end them, we're going to see that its dimensions have changed. Interesting. What did I do? My keyboard got locked. Give me a second, everyone. So it's not my keyboard. All right. Okay, I'm back. We can go to dot endem. And if we run that, we can see that the dimensions changed to now be a singular 3. Before it was a dimension of 2. Now it's a dimension of 3. That's because I nested it inside of another tensor. All right, so that's the unsqueeze. Next, we have ravel. Let's hear it.
So the unsqueezed just adds another dimension to the list. It adds that in this case the third dimension. So like it's a list nested in a list nested in a list.
Exactly. Just
Okay.
putting another box on top of it. All right, so now we go to tensor 1 dot ravel. Now let's take a look at this ravel tensor. Now we had a tensor that was 1 by 3, but by running the ravel command, it just turned it into a one-dimensional tensor, which is just 1 by 9. I put it all together. Again, all of these methods are constructive, not destructive. They are not manipulating the original value of tensor 1. They are all being saved under a new variable. All right, so now let's go into our reshaped tensor here. Let's hear it, Demi.
So it's just doing the same thing as the dot view, right? That ravel, or is it something different?
No, so the ravel is the output was the same as the dot view, right? If I come back up to dot view,
You just passed it.
yeah. If I
Okay.
come back up to dot view, right, that is the same outcome. It's providing the same outcome. But notice that in dot view, I have to provide some sort of explanation as to what I want to do, right? So I had 9 different values, and I told it I wanted to do it 1 by 9. I could also do something where, hey, instead of doing 1 by 9, I want to do 9 by 1. And when I run this, it would give me a tensor of 9 separate tensors, right? So that's the difference between view and ravel. Ravel doesn't give me that option. It doesn't take any arguments. It says, hey, if you want it to be a 1 by 9 or a one consistent tensor with all of the different inputs, you could just run ravel and it will automatically do it for you.
Gotcha. Okay. Yeah. Thank you. Appreciate it.
All right, so here we have our reshaped tensor. Now we can go take a look at our reshaped tensor by seeing it through VS Code. And I messed something up. Tensor 1 dot reshape 1 by 4 reshape tensor. It's invalid. Input of size 9. Let's see. Oh, well, that would make sense if it's an input of size 9. There you go. So reshape works almost like the view, all right? Where we can feed it something and we have to specifically tell it how to format it. All right. Now we're going on into the split method. So split tensor, which is just a tensor1 dot split with dimension, in this case, 0. Let's take a look at the split tensor now. So now you can see that what it did is it split the tensor. It returned it as a list of tuples, but I could also do something like T1, T2, and T3. And then I could take a look at any one of those, right? So T1 would work where it just shows one tensor. I could get T2 as well, right? It essentially took that one tensor and completely divided it into 3 independent tensors. All right. Moving on into some mathematical operations. So now I can say, hey, I want the sum of the entire tensor. Well, that would just be tensor1 dot sum. And we could also grab the mean of an entire tensor by doing tensor1 mean. So let's take a look at the sum. So the sum of tensor1 is 45. And the mean of tensor1 would be 5. All right, so there's our two different functions there. We've seen the aggregation function, but we can take a look at it one more time. So here we have tensor, excuse me, let's go with max val and max index. And this is going to take tensor1 dot max at dimensions 0. Now let's take a look at that. All right, when I run this, it tells me, hey, the max value for tensor1, or excuse me, the max indexes for tensor1 fall in 2, 2, and 2. So if I come over to tensor1, oh, tensor1 is way too high. Where are you at, tensor1, tensor1, tensor1? Here you go. You can see that the max value here at index 2 is 3. At index 2, it's 6. And at index 2 is 9. So there's my max index. And then it gives me the values for them, which is 7, 8, and 9. Or the max value tensor would be the tensor holding the most weight, which is 7, 8, 9 at the very bottom. All right, so those are the different things for tensor.max. All right, the last thing that we're going to be covering is going to be transformation. So here we're going to open up a tensor block. There's going to be a transposed or transform tensor. This is just going to call tensor1 dot t. And now let's take a look at what it looks like. So now instead of being 1, 2, 3, 4, 5, 6, 7, 8, 9, it took the tensor and put it on its side. So now we're 1, 4, 7, 2, 5, 8, and 3, 6, 1. Right? It just essentially flipped it 90 degrees. All right. I see a question from Jacob. Let's hear it.
Uh, yeah, back with your max value and max index, I think I missed it. Does it automatically sense, like, based on that naming convention that you want it to be an index and a value? I'm not really seeing where it can kind of tell that you're trying to return indices versus values. Does that make sense?
It does, yes. So when I run max, max returns a tuple. And that tuple in index one will hold a tensor with indexes, or excuse me, with the most cumulative, that's a big word for me. Yeah, and I messed it up. Value. And then in index two, it will return a tensor for the highest value in each tensor. Right? So if we take a look at our tensor one, so tensor one is holding 1, 2, 3, 4, 5, 6, and then 7, 8, 9. Right? So the first thing that it returns is the max cumulative value. Well, 7, 8, 9, that's going to be 24. And this one is only 6. And this one is only 15. So 24 is going to be our max value. So that's why it returns for max val 7, 8, 9.
Okay.
And then the second tensor, it's looking, hey, which index holds the highest value for each one of these tensors? Well, at index 2, we have 3. At index 2, we have 6. And at index 2, we have 9. And that's how we get the max indexes for each one of these tensors is 2, 2, 2, and 2.
Yeah, I get that. I guess I was just kind of confused of like the how it knows, I guess, that you're trying to return the indexes. I get that, like, each index is at two is the max values. Um, I'm just, I'm just wondering, I guess, how, like, if it automatically just returns like index and a value, I guess, is what I'm saying. I'm just trying to understand how it knows that you're looking to return the indices of that from max.
Got it. Yes, that's just its default thing.
Oh, okay.
Default behavior will be to always return a tuple with those two. One, the max indexes, and two, the max value,
Gotcha. Okay. Thank you.
of course. All right. Well, that's going to cover our entire tensor introduction and tensor manipulation, getting set up with Jupyter notebooks, and ensuring that we were able to install PyTorch, understanding a little bit of the language model system, which we're going to do a deep dive into here in the next coming days. Does anyone have any questions over any of the topics that were covered today? All right, no questions. Fantastic. Is everyone fried? Is that what's going on here? Okay.
I just have no idea what we're gonna do with this information, how to make it usable. That's I don't know. I've never delved into this stuff, so
Yeah,
kind of
no, absolutely. It's an exciting thing. We'll be diving into it here shortly, and I'll be sharing a YouTube series with everybody, and that's kind of going to be our afternoon work time. It's just watching that video. That way, it can make a little bit more sense. All right, awesome. Thank you so much, everyone. Let me go ahead and stop our recording here.